Well, hello again. Welcome to week 3. This is the week when I'm going to be talking about environmental noise pollution. And we're going to start with some work on the physics of noise. I'm going to use Anna's lecture notes from last year. And thank you, Anna. They're I think, rather better than the lecture notes that I produced when I taught this unit a number of years ago, or in 2017, I last taught this unit. So these are Anna's notes, and thank you. So I'll comment on them. And in this particular session, we'll be talking about the physics of sound, and that includes frequency and wavelength. We'll look at decibel scales and how sounds can be added. We'll look at the measurement, and we'll look at what we call weighting scales, a weighted scale, units or measurements reported as dBA, and I'll explain what that means. Then another thing we need to look at is sound power, sound intensity, and then briefly a subject called psychoacoustics, which is about how the brain perceives sound that the ears hear. And then I'll just start my introduction to noise and talk about hearing risk. So we're going to start with the definition of sound. Sound is a pressure wave which can travel through solid, liquid, or gas. We're particularly interested in sound transmission through air and sound that's detectable by the human ear. So like all waves, there's an amplitude and there's a frequency. And as far as our hearing is concerned, the range of frequency in a healthy, young, adult human ear is from around about 20 hertz to, that's 20 cycles per second, to, well, it says 20, but that's probably an overestimate, probably 14 or 15 kilohertz. So associated with the sound wave, there's a wavelength, and that's significant from an environmental point of view, which we'll talk about later. And other animals have a different range of hearing. Dogs can hear at a higher frequency. So making sounds, making music. I'll give you some examples of this. No doubt some of you have learned or are still playing a musical instrument. My main musical instrument is a cello. I'm not going to bring that along. So during the class, I'll bring along a couple of musical instruments and we can have a look at them and just see how they work. And there's something about nodes and antinodes, and I can demonstrate that very clearly on a wind instrument. Fundamental frequencies and harmonics. That has some importance in environmental acoustics because it's possible for a fundamental frequency to be generated which is not able to be heard, but that can resonate and produce quite large levels of sound in the audio frequency range at higher frequencies. So we talk about a spectrum of the sound, and that is the relationship between the amplitude and the frequency. And on this graph here, you've got the vertical scale is the amplitude, the horizontal scale is the frequency. And you can see that that particular sound has peaks at multiples of certain frequencies. And the other thing that demonstrates is that if you have two tones close to the same frequency, they can generate what are known as beats. And I'll demonstrate that to you in class as well. So sound is measured with a sound level meter, but it actually measures sound pressure. And one of the things we can do with most sound level meters is to get an estimate of the spectrum in what are known as octave bands. An octave is it's a musical term, but all it means is that it's a doubling of frequency. And it has frequency bands, and they're centered on different frequencies, 31.5, 63, 125. Ones we're particularly interested in round about 250, 500 to 1K, which are the sounds of the frequencies of human voice. So if you are interested in being able to hear people speaking, you would be looking at noise in that fairly narrow bandwidth between 250 and hertz and 2 kilohertz. We come to the next thing, and that is filters. And normally there are at least 2 and sometimes 4 filters built into sound level meters, A, B, C, and D. And the use of those, it's somewhat historical. For example, the C filter was introduced to measure noise from piston-powered aeroplanes. But it's quite useful in that, as you can see, it's fairly flat. So if you have a sound level meter with a C filter attached, that will give you pretty much a flat reading of sound pressure level. In other words, the frequencies will be recorded as sound pressures, or the sound level will be recorded as sound pressures over the range of the equipment without any filtering. Now, the A level, as you can see, attenuates the sound at low frequencies. And the reason for that will become clear in a slide further down when we look at the psychoacoustic effects. There's a Broad Care sound level meter. That's a fairly old meter. It's fairly heavy. The more modern ones are lighter. So the range of sound pressure level is quite large. The range that we can hear is quite large, over about 10 or 12 magnitudes. So to avoid having a whole lot of noughts in our measurement, we introduce a decibel scale, and it's simply the 10 log the ratio of the square of the sound pressure level over a reference sound pressure level. And that reference level is around about the lowest or quietest sound you can hear. Now I've put these notes in here to indicate that when you're adding two waves of different amplitudes, then you can have the sum will depend on the phase. But if you get away from sound pressures which are the same frequency, then phase doesn't matter. So you're just adding it's the sum of the squares of the frequencies. So when you take the log of both sides of that equation, you get this rather complex equation here. And just to illustrate, if you had two sound pressure levels of 80 decibels, their sum would not be 160 as you might expect, but it is 83. And here's another slide giving the same result. And as a rule of thumb, if the difference between the levels is less than 1 dB, then you can add two sound pressure levels and the sum would be 3 decibels higher. Now we need to talk about sound power. If you're starting to do calculations based on, let's say, the noise emitted from a fan, an air conditioning fan on the outside of a house, you would start with the measurement or the determination of the sound power. Now, quite often you'll find that catalogues or the maker's specification will give you the sound power. But don't confuse that with sound pressure. So we'll be in class looking at the detail of how you can assess sound pressure at a distance. And it depends on all sorts of things, like whether or not the wave is reflected from the ground or it's reflected back from an inversion in the atmosphere, whether there are attenuating trees or barriers in between the source and the listener. So that's all to come in the next part of this course. So there's a nice little summary of the 3 units that you might be concerned with: sound pressure, pressure in pascals or newtons per square meter, sound power in watts, and sound intensity. And there's a nice little analogy here between sound and heat. So I mentioned earlier psychoacoustics, and that is a very famous curve or set of curves called the Fletcher-Munson curves, and they're plots of equal loudness. And that was done by a series of experiments in which a large number of subjects had headphones on, and in one ear they were played a sound of frequency, I think it was 500 hertz. I'm not too sure about that. Let me just have a look at this and I'll see if I can. Anyhow, I need to check that. No, it was 1,000 hertz. That's right. So they were played a sound of 1,000 hertz, and in the other ear they were played a sound at a different frequency. So if you look down at this curve and you look at 100 hertz, you'll see that the sound level had to be rather higher at that lower frequency than at 1,000 hertz. And if you're looking at the 40 decibel or the 40 FOMs, then you can see that from that curve, the sound level at 100 hertz has to be 40 to about 20 decibels higher. So that was the basis of the A weighting curve. They, in effect, inverted that red line there to give the A weighting curve. And what that means is that because the ear perceives sound levels at a lower frequency as relatively softer, then the sound pressure, or the instruments that are being used to measure sound pressure have got this weighting curve to weighting filter to give you the same psychoacoustical effect. So we've been talking about sound, and you can distinguish that between sound and noise. And the only difference, of course, is that noise is something that you don't want to hear. And that is what we're all about with environmental acoustics. And sometimes the difference between sound and noise is very much subjective and in the ear of the beholder, so to speak. And then we have the hearing risk problem. And there's a whole lot of work has been done on safe levels in the workplace. And essentially, if you have a sound pressure level, or if you're subject to a sound pressure level in excess of about 90 dBA for an 8-hour period, you are going to have permanent hearing damage. Now, 90 dBA is not very loud. My voice in a classroom, you might be able to measure this. In fact, what you can do is download a very, a free app, sound level meter for your phones, and you can measure the sound level in the classroom. It would normally be about 50 or 60 background noise level. And when I'm talking at a reasonable level, it would go up to 70 or 80. So if you're listening to me for 8 hours, you're likely to get permanent hearing damage. And there are all sorts of effects like spikes and the spectrum and so on. And as I mentioned, there's a trade-off between sound pressure level and exposure time. And there's one of the methods of assessing the risk to hearing called a partial noise dose. And finally, we look at noise level descriptors. And if you have a sound level meter and you're taking a continuous recording, then you can run that data into a calculator and or into particular circuitry in the meter, and you can come up with an L10, which is one of the descriptors. It's the level, well, it indicates that the sound level has been above a certain level of dBA for 10% of a particular time period, as illustrated by that graph. And there's a concept of background noise. And we'll talk a bit more about background noise when we're looking at legislation. And I just put this slide up here because background noise can result from all sorts of sources in a room. And one of the interesting things is that if you have a room, you probably haven't experienced this, but if you're in a room with very, very low levels of noise, down around about 20 or 30 dBA, it's quite uncomfortable. And for that reason, most workspaces which are acoustically insulated from the outside and would otherwise be very quiet, noise is injected into these workspaces to bring it up to a comfortable level. This might be, you don't know it, you're not aware of it, because it's a noise generator and it's a sort of hissing noise that you can't really hear, but it does bring that level up to so that you're not hearing people sort of shuffling their feet, or you can't hear your own breath or the noise in your own ears. So the other way of doing that is to inject music into a space. And in some areas where people are working or shopping and so on, there's a bland type of music called music, which is generated, and it just makes people feel better. Well, I think that's the end of this session. Pretty much. Harmful noise, we've talked about that. 85 dB or 90 dB, roundabout. There's an argument as to whether it's 85 or 90. And finally, some of the harmful effects of noise pollution. We'll be talking more about that in the next part of this series. So thank you for your attention, and I'll see you in the next part.